So it's easy to forget where we started out with in this chapter. We were talking about there's 3 kinds of bonding. There's ionic bonding, covalent bonding, and metallic bonding. And so we talked a little bit about ionic bonding, and we spent a lot of time talking about covalent bonding, and now we're tacking on this little bit about metallic bonding at the end. This is the electron C model. So here we have sodium atoms. They're metals, though. Metals have low ionization energies. It's very easy for them to lose electrons. So what happens here is the sodium atoms will lose an electron, essentially becoming an ion, and send that electron out to play, basically, right? The little purple, those are houses, and this blue, this is a bunch of little boys running around playing together. There's an attraction between this negative electron C and the positive ions, and that's what holds the metal together. And it's not a directional bond. It's the ions are attracted to the electrons all around them. So that explains malleability and ductility. So if I apply a force, like I smash this with a hammer, it's going to dent. It's not going to shatter. Because if these move a little bit, it's okay, because that sea of electrons moves also. It also explains conductivity, both of electricity and of heat. These electrons are free to move. They're not tied to a single atom. And so the electrons can move, and that carries, that's electricity, is the movement of electrons. And the movement of the electrons is actually what primarily distributes the heat as well. Any questions?
Did we name electrons before we named electricity?
That's a good question. Which word came first, electron or electricity? I don't know. We should look that up. And then this slide, I think is just interesting from being an Earth person and living on the planet, right? So what's up with the ozone, right? So oxygen has a double bond. So oxygen looks like this, and ozone has that weird resonance structure. It kind of has a 1.5 bond. It's a bond that's intermediate between a single and a double bond. So this bond is weaker than a double bond. A single bond is weaker than a double bond. Something between a single and a double is weaker than a double bond, right? So high up in the atmosphere, we have an ozone layer. There's ultraviolet light coming in from the sun. Ultraviolet light has enough energy to break the bond in ozone. It can't break the bond in oxygen because that bond is too strong. So it can break this hybrid bond in ozone. Well, what do you get when that happens? Well, you get oxygen molecule and an oxygen atom. But that process absorbs that energy. So that energy then does not go through to hit the planet. Ozone does not absorb all the ultraviolet light, but it absorbs a lot of it. So then what happens to the oxygen molecule and the oxygen atom? Well, this oxygen atom is really not happy, and so it's going to recombine to form ozone again. The reason chlorofluorocarbons are bad is they disrupt this cycle. They mess it up. And if we didn't have the ozone layer, we'd be getting a lot more ultraviolet radiation, and it would be a lot more dangerous to go outside. I don't know what the level is, but you might not be able to go out at all without sunscreen or an umbrella or something. Any questions about that? See, we can talk about this now because we've talked about how light is energy, right? And amounts of energy vary with the frequency and the wavelength. and we just talked about the strength of bonds, this bond being a little weaker, the ultraviolet's enough. Visible light doesn't mess with it. And so you think about the planet and you start learning about some of these very fine-tuned things, right? This is just the right energy in this bond to absorb ultraviolet. But it doesn't absorb the light, the visible light. It just absorbs the ultraviolet light, which isn't good for us. You know, this is really pretty cool.